to chapter 16. Yeah, just turn to chapter 16. I just want to take a look at that. Okay. All right. So this is where we're headed after we do your study. So I wanted you to have information on this, and on your next assignment, once you complete your chapter review questions, you can go ahead and look here. Okay. So this chapter will be in it most of the semester. Linkages, cams, gears, and bearings. Oh my. All right. So just wanted you to look at it, eyeball it, see that the first part of it is on mechanisms and linkages, and the types of little schematic drawings that we're going to be doing. So just a few pages on linkages, but lots of drawing to do, and they're simple looking, but they're pretty involved, and it'll work your brain a little bit. And like I said, we're going to build some models of them with either popsicle sticks or cardboard or whatever. We'll make our own little linkage contraptions. Okay, so all right. So those of you that are listening by radio, Cassidy, recording this for her as well. I'm showing a, oh, well, I can put it on here. Yeah. Little contraption. Well, it looks funny on this video. Looks like it's made out of rubber.
Yeah, it kind of does.
Watch it. Well, it's not bending. It is just a piece of cardboard. Okay, so figuring out your motion and what you want to do with your movement. All right, so let's flip over to chapter 4. And the first section is on materials. And just prepare yourself. Please make yourself a schedule for studying this and reading it right away. All right, so there's a lot of information in here. So materials broken down into ferrous and non-ferrous metals, and then we have plastics, which there are thousands of different compositions of plastics. All right, so looking on page 122, which you'll be reading, studying, you have ferrous, non-ferrous, plastics, or polymers, and underneath there are thermoplastics and thermosets. Then we have inorganic materials, carbon, ceramics, and composites. The tensile strength, the ability to be stretched, and they have high compressive strength. And then, oddly enough, increasing strength at increased temperatures. It's interesting. You'd think something get hotter, it's going to get weaker, not as tensile. But you heat it up, it becomes stronger. Okay, able to resist stretching. Okay, or the ability to be stretched. So it kind of goes together. You can stretch it. You know, if you think of chewing gum, you can stretch it pretty easy. So if you get the chewing gum hot, it stretches pretty easily. Okay, so the same thing happens with these materials. Okay, it's kind of a physical standard, a physical quality. Then composites, where we put two or more materials together, and there are more and more composite materials. I went to a rapid manufacturing conference and got to tour a facility that uses composite metal, powdered metal, mixed together and come up with all kinds of different alloys that way, just by mixing powdered metal together. So like titanium and aluminum, that you normally couldn't melt both of them and mix them together, but you do them as a powder and then put them together and heat them up, and they can bond and come up with some really unique characteristics. Okay, so you'll study through the anything that's ferrous and what determines it as non-ferrous. What's the word ferrous mean? It's a trying to think if it's a Greek word or not. I can't remember. It's root. But at any rate, root word, where it comes from, its etymology. So it's basically anything that has iron in it, ferrous.
Right. Isn't that FE on the periodic table?
Exactly. So on your periodic table of elements, give it a little. I just love this chart. Never taken a moment to look at it. It's up here on the board. Maybe I can scan it in. Okay, so all the elements and a little example of the elements, you know, where they can. Of course, if it's a gas, it's kind of hard to put it on here. So, like for helium, though, they've got it in a kind of a glass tube neon sign kind of thing. It's kind of neat. And then hydrogen, of course, is a gas. So they show images from the Hubble space telescope, and so these are, you know, the foundations of our solar system, of our universe, is hydrogen. It's the most basic element, the lightest. Okay, value of 1. Okay, on the periodic table. So let's see. Good heavens, I forgot the number. 6?
26.
26. Right there. So there's a piece of iron ore, a chunk. Now, iron occurs out there in the earth. It's one of the most common elements. It's in clay and dirt, right there in your yard. Now, small quantity, but it's there. Okay? So anything that's ferrous, okay, has iron in it. So all of your steel, alloys, and so forth, and the different compositions of it, then it's classified by how much carbon it has in it. Okay? So the more carbon it has in it, the more brittle it is, or stronger. Okay? It doesn't take very much. So a common steel that's used in mechanical design, cold roll steel, is like a 1020 classification, it's called. Okay, so the 10 represents steel, okay, and then the 20 represents the 1/10% of carbon per volume. So 0.2% of carbon it has in it. So you add more carbon, it becomes a stronger steel. So they'll use it out here in manufacturing, you know, to cut other lower grades of steel. They'll increase the carbon content. So it's just a speck. It's amazing just what a small amount of carbon will do to steel or do iron to make it stronger, okay, and change its characteristics completely. All right. Then there's stainless steels, where it has at least 10.5% chromium added to it. That's a lot of chrome added to the steel alloy, and prevents it from rusting. Okay, so it can be used in wet environments and not decompose or rust. Okay, restaurant, hospital equipment, marine, you know, near docks and rivers and lakes and oceans, stuff like that. All right. Then you'll look at the steel numbering. Everything. The SAE, Society of Automotive Engineers, has classified steel for us, and these are the different types of steel. Okay, different alloys. So there's the 1040. That's a forging. See, we've gone up from 1020, and 1020 I don't think is listed on here. There's an old lock washer. Okay, it's 1060. Okay, so old cold roll steel, 1020. You know, it's really soft and malleable and can break it pretty easily in relationship to other steels. Okay, so you'll read and study about that numbering system, and you'll have some pretty detailed questions about that in your study when you're doing the review questions. Non-ferrous metals, okay, do not contain iron, and wherever we need applications where steel would be a problem as far as its weight or magnetism, sometimes you can rub two pieces of steel together enough and they can become magnetic. It's pretty interesting, you know. So aluminum, and we'll look at I'll post you some videos on how steel is made and how aluminum is made and so forth, just, you know, for your reference. You won't be tested over anything, but you might want to look at these. And then copper. Okay, copper is an element. Cu is its signature. See if I can find it. Copper is heavier. There it is. So it's a weight of 29. I'm showing a glob of it. Doesn't look like that in nature. Okay, it's in a rock, and it's usually green looking kind of stuff. You've seen buildings with green roofs, maybe church spires or buildings that have copper on it and they're green. You know, if they're not coated, then the oxygen in the air makes them turn green. Okay, so it's not a bad thing. It doesn't look all that pleasing. Some people like it. I'd rather see the bright, shiny copper look. But anyway, the green oxidation that happens to it actually kind of protects itself. Once it's on there, it forms a layer of protection. It doesn't go any deeper. It doesn't keep like steel would, but on the other hand, they've also figured out, you may have seen some bridges or steel work that's all rusted. I mean, it's totally rusted. They actually design it that way so that it's rusted up and it actually protects itself. You don't have to paint it. You don't have to do anything to it. It builds up a layer of oxidation on it and it stops. It doesn't rust anymore.
I think that's what they did with the new basketball stadium they built in New Jersey.
Oh, okay.
They,
Just let it rust.
yeah.
And as opposed to some older steels, different compositions in it, like our bridge that's closed, our blue bridge here in Owensboro, and they're painting it, okay? Because it would just, the way it's composed and alloyed, it would just rust completely through and deteriorate. It would go all the way through it, you know, and rust in two. That's why they make battleships, and they coat them with a pretty thick coat of protective paint, you know. Although the steel on a battleship or any kind of ship could be 2 inches thick.
Double layer.
Yeah. Water towers, they're made out of steel. Okay, and most of those are painted. But on the inside they're not. And the water's in there. Okay. So you'd think, man, it'd just rust completely out. But because there's a limited amount of oxygen, it usually doesn't, you know, rust all that much on the inside. And water contacting it, water doesn't have a whole lot of oxygen in it, so it doesn't deteriorate it. Water is made up of hydrogen and oxygen. Okay, so it doesn't react with it as bad as you would think. So all your water towers, they're not painted on the inside. They're coated or in any way. The water tower on Parrish Avenue, I know a lot about because I trained the guys that installed it, that built it, in how to read blueprints. He had a whole crew and they'd never had blueprint reading. And they'd already built 2 or 3 big water towers, you know.
Feel confident there.
Yeah, but basically the supervisor was having to tell them what to do. But anyway, I'm telling you about that because I know that is like 1.5 inches thick steel. Holds 1 million gallons of water. Okay, so, you know, comes in the non-ferrous metals, wherever we need, you know, conductors, or we need a certain look, a certain color, different qualities. So you got brass, which is an alloy of copper and zinc. You got bronze, which is an alloy of copper and tin. Okay, tin in small qualities makes it hard and increases the wear resistance. So bronze statues, you've seen statues cast out of bronze. Okay. Brass is another one because it has quite a bit of copper in it. It's 90% copper. You know, it'll turn green. It can, but they'll usually add some other alloy content. You know, like zinc. It's 10% zinc. So it's copper and zinc, and that helps it from turning green. You know, over a long period of time it might. Then you got specialty metals: gold, silver, platinum, columbium, titanium, and tungsten. Now, platinum I discovered this summer, I didn't know this, is not from this world, is not from the earth. It come from outer space. Large meteors hit the earth in its early life. A lot of meteors, you know, and so the platinum that we have comes from outer space, somewhere out there.
Like when they killed the dinosaurs?
Well, I don't know when. I'm sure it was well before dinosaurs. It's early in the Earth's life when it was forming and had not much of an atmosphere. Okay, and a lot of meteors burn up before they get here, and then the large ones that would have hit. So apparently, you know, like in South Africa, is a lot of platinum. So apparently, some meteors, a whole range of them must have hit down in there that had a lot of platinum in them, and got into the earth and, you know, covered up over time, and then we mine it. Okay. There could be some of these others too, but all right. Then you'll look at the numbering system. That's a unified numbering system, UNS. It's on page 126. I'm still, after all these years, I'm still getting used to that numbering system. I'm used to the SAE numbering system, but you'll see the UNS numbering system used as well. Okay, now let's see where I'm at. Then we look at plastics and polymers. You'll study about those. And a plastic is a complex, organic, polymerized compound capable of being formed into a desired shape by molding, casting, or spinning. To a lesser degree, plastic also can be cut and shaped, but it's not nice. Okay? It retains its shape under ordinary conditions. Polymerization is a process of joining two or more molecules to form a more complex molecule with physical properties that are different from the original molecules. So when you make a polymer, or you hear the word polymer, that's what's happened. Through chemical or mechanical process, they've joined molecules together and create something different than what they were on their own. And that happens, I mean, you know, with steel and non-ferrous. We bring different elements together, and when they're joined together, it creates a new type of element, not a new type of element, but an alloy or a compound that has different characteristics than either one of the original, or better characteristics. Okay? So plastic and polymer sometimes are used, you know, interchangeably, and they will be a lot of times in the book. So then a study about thermoplastics, and man, you can see, I mean, you know, acetyl, acrylic styrene, acrylonitrile, ASA, acrylonitrile butadiene styrene, ABS. That's what I use back here in this machine. And ABS is used in your automobile, more than likely your computer monitor there and keyboard, and a lot of the parts in the computer case, your laptop. I mean, ABS is widely used. All right? So it's commonly used because of its excellent impact strength, reasonable cost, ease of processing. Okay, so it can retain its dimension above 212 or 100 degrees. Usually, most of the compounds can. Then there is cellulose, fluoroplastics, ionomers, liquid crystal polymers, methyl pentanes, polyacetyl polymers, polyamide, which is nylon. Okay, that's used out in manufacturing. Lots of components are made out of nylon. It's tough, it's strong, and abrasion, heat, and friction resistant. It's a really neat composition. Polyerlate. And it continues. Polycarbonates, polyether, the ketone, or peak. Okay, so there's a lot of use of that actually out there, electrical components and stuff, aircraft parts. Polyethylene, okay, used for chemical, petroleum, and food containers. So when you buy those Glad containers, it's made out of polyethylene, saran wrap. Polyethylene oxide, polyethylene sulfide, polypropylene. Okay, so resistant to continuous bending, appliance parts, hinges, cabinets, and storage containers. So those big crates that you buy at Walmart, you know, and you put all your junk in it and seal it up, put it in the attic, find it 10 years later. Anyway, so polystyrene, polysulfonese, polyvinyl chloride, PVC, so your water pipes, hoses, sometimes even parts of your tennis shoe. Thermoplastic polyesters, okay, strength and good electrical stress, chemical resistance. And a polyester form of that is used, not a thermoplastic, but a form of polyester, used in clothing. A lot of your clothing is a blend of polyester and cotton or other types. Thermoplastic rubbers. Then thermosets, they make up about 15%. They're more brittle, cannot be remelted once they are molded into shape. Wow, interesting. So once you form it, it works one time. I'm not sure what happens to it afterwards, or what it looks like. I think it just burned. It'll do it one time. Thermoset. Okay? So you have alkalids, melamine, phenolics, unsaturated polyesters, urea, formaldehyde. Then elastomers, they're elastic, much like rubber. Okay, so you have butyl rubber, chloroprene rubber, which is neoprene. A lot of your shoes have neoprene soles, okay, or a form of it. Chlorosulfonated polyethylene, epichlorohydrine rubber, and so forth. Do you have to remember all of these? Jared says no. Okay, that's true. I'm not going to ask you to take a 2,000 question matching test or anything. But the major ones on each of these types of materials, yes, you do need to recognize them. Okay? All right? So the major ones, wherever you read and it says commonly used or, multiple uses, all right, you'll need to be trying to memorize those, like ABS, okay, polystyrene, this type of thing, all right? Definitely the big broad categories, all right? So ferrous, non-ferrous, plastic, polymer, elastomers, okay, all of those types of materials. Then we have plastic resin code that you'll look at. And there's two different industries that have standards for those. You'll finish the study with material selection. So, selection of aluminum. You'll need to be able to tell me why you would make something out of aluminum, why you would use aluminum, and be able to list some of the characteristics of aluminum. Okay? Examples of the aluminum numbering. Then, the examples of steel numbering applications is on 124, 126, which we briefly looked at. Machinery's Handbook, which there's a copy up here, and there's some back there on the shelf. And when you graduate from the program, if you're an honors student, you'll get a copy of Machinery's Handbook if you don't own one already. But you need to know Machinery's Handbook. You need to look through that. It has all of this information pretty much in there that we flipped through. Okay, it's in different charts and tables and so forth, but it's a ready reference. So this is another reason why you want to hold on to this book that you have in front of you, and keep it if you're going to stay in the career. Excellent reference material. All right. What's that? Oh, well, I'm done. I'm on page 134. I think I said 135 in the assignment, but it really stops here. Okay. Now, in Inventor, you can design stuff in Inventor, and you all experimented with this a little bit. You go in there and actually choose the type of material you want to work with and design with. And so learning, I think we went through a little lesson on that in Learning Inventor, and this kind of goes over it in a little more detail in a generic sense, but the tables of characteristics, that is how much it weighs per cubic inch or square or cubic millimeter, I think is what it goes down to. You can look that up. So if you wanted to use a specific alloy, then you look up the physical characteristics of it in Machinery's Handbook, and you can type that information in, and then in Inventor you're actually working with that material. And if you do an assembly, you can ask for the physical properties, how much it weighs. You can do a study on its tensile strength, because you'll put in the modus of elasticity and tensile strength and so forth. You'll load that information in there into Inventor. Now, a lot of it is already available, but if you're working with something that's not listed, you'll have to key in that information. Okay, so I ran a little bit over, but very necessary to do. Yeah, in Chapter 3, they kind of show some analysis that can be performed using the program in Inventor. So you can actually place a load, a stress on a particular arrangement of the part, and it'll give you a color display of its stress points and what you need to do, where you need to thicken or strengthen so that the forces are distributed more evenly. You don't have a stress point or a break point. All right? So in your CD that comes with the book, most of you have downloaded that perhaps to your desktop, you know, which you can copy the CD to your desktop, or you can just run right off of the CD. Yeah.
How long is this all gonna take? Because I got a class at 9:30.
Yeah, I'm basically done. Okay. So sorry I ran over a little bit. So you have your assignment, and your questions are on the CD. So let me refresh my memory real quick here. So you got 77 questions to answer, 1 through 77. Okay, so you can see a whole host of them. 42 to 57 is basically identifying the type of metal that are with that. So basically looking off of the chart, it's just making you run through that. Remember, you are to state the question in italics and then put your answer underneath in each case. Consider this an open book test. I'm actually not going to test you over this, okay? So what you're doing is you're studying, and I'm just going to count it as one of the tests, okay? So it's due next Wednesday. And be ready to rock and roll on linkages next Wednesday. And I've got to run to the used coffee department.